Let's get started here. It's my pleasure. This is the first chaos seminar of the semester here, so welcome. It's my pleasure to introduce Jase Bernhardt, who comes to us just down the road at Hofstra University, the Department of Geology, Environment, and Sustainability. Maybe this is a future for our name. Jase actually just started there about a year ago, and so he's a tenure-track assistant professor, and so forth. And so I thought it'd be a good idea for him to get to know us a little bit, for us to get to know him. He's relatively close. Just a little bit of background on Jase. He got his Bachelor of Science in Atmospheric Science at Cornell. Then he went to Penn State, where he got his master's and PhD in geography in 2013 and 2016, and so forth. He's done a variety of things, but the one thing that caught my eye on his CV is that while at Penn State, he did win a number of outstanding Best Student Paper Awards, at least twice I saw there, and also an Outstanding Teaching Award while he was there in the department, even as a graduate student. He also won a Best Student Paper at AMS History Symposium, I saw in 2016 at the annual conference there for AMS. So that's very impressive. He has a number of papers, and I asked him to talk about some of his recent work, I think from your PhD,
yep,
and so forth. So let's welcome Jase here today.
Great. Thanks a lot, Brian, for inviting me out here, and everyone for having me here. And as mentioned, I'm at Hofstra University, just beginning my second year there. And apologies in advance, my voice becomes hoarse later on. I just returned from Japan a few days ago, so body's still a little skeptical of this new time zone, but should be able to get through this. So today I'll be talking about, as Brian mentioned, work done towards my PhD dissertation and some papers that are in various stages of submission coming out of that. So this all kind of built out of a very simple concept revolving around the basic question of how do we think about averaging daily temperature. And as we all know, temperature is the very key weather variable we all like to measure and talk about and analyze and debate its change. And of course, the initial history of all this with thermometers and temperature measuring was that in the last few centuries, important instrumentation was built around trying to kind of maximize the data you could get from manual observations. So one very important piece of technology was the maximum and minimum thermometers that were made. And those kind of gave you a good bang for your buck because the thermometer would show you both the max and min temperature for the day, so 2 data points, when checking it just once per day or once per 24-hour period, depending on when you consider your day to be midnight to midnight or 8 a.m. to 8 a.m. or whatever time slice you use. And therefore, we of course began the tradition of computing our, quote, average daily temperature as 2 simple data points, the maximum and the minimum divided by 2. And of course, here in the US, we like to be different, and that's in degrees Fahrenheit. Since all this work was done in degrees Fahrenheit, even though it's not, of course, a tradition. And we know in recent decades, we've now transitioned away from the old school manual handwritten observations to, of course, using our new technology to use automated weather stations, measuring temperature around the clock, sometimes every hour, and of course, more recently, you have data being recorded at the minute or even seconds interval. And initially, this was motivated by increased air travel, so hence a lot of weather stations, the important weather stations, are at or very near major airports, because, of course, weather conditions and forecasting go hand in hand with being able to successfully fly planes. And again, this is all automatically being reported now, and no longer do we have this need for the manual observations and the usage of the twice daily measurements. However, our automated stations, at least for the official capacity of climatological reporting, still use the traditional max plus min over 2 temperature averaging method. So despite the fact that we have the technology and we have the actual observations giving us much more data per day, we're still stuck in this old school way of just using 2 data points to then estimate what happened across the entire day. And here's an example of one of those older thermometers where, for example, you could have 2 bulbs and one leaves a mark where the maximum where the mercury rose to a maximum, then another to the minimum. You reset once per 24-hour period, and again, you get those two measurements, high and low, max and min, and then away you go with your daily average temperature. Of course, this method of averaging your daily temperature has the very faulty assumption of a perfectly symmetrical or bell-shaped curve of your daily average temperature. So if this was the case, and of course nothing is ever perfect in the climate and weather world, it would be fine to do max plus min over 2. But as we know and expect, it's really the case where you have a perfectly symmetrical rise and fall in temperature each day. There's various reasons why the temperature does not follow that. So hence, the traditional method is using the incorrect assumption that we have a symmetrical curve, but in fact that's not the case. So it's the first example here. I'll pick on where I'm from originally, upstate New York. So here's the average daily temperature curve for Albany, New York for the past 30 years, the 1981 to 2010 climate normals periods. This is just average every day of the year annually. This is what the average daily temperature curve looks like starting at 5 a.m. where you have the hourly minimum and then off for the rest of the day. And we clearly see this is an asymmetrical curve. So just for this one station, we see that if you assume T max plus T min over 2 is going to give you an accurate representation, well, that's not going to be the case because you don't have that perfectly symmetrical curve as asymmetry present here. So this kind of leads into giving you a flavor of some of the previous work that has been done surrounding this issue. There's been various studies, both at very small scales, looking at individual stations, also large scale, looking at many, many stations, some using pure observational data, but many others using reanalysis data, which maybe can be problematic. So here's an example of just a study looking at a single station using actual observational data to kind of attack this problem of comparing the traditional method, so T max plus T min over 2, over what should be a more accurate method, which is, of course, hourly averaging. So 24 data points versus 2 data points, now you can start to capture that daily temperature curve and that asymmetry in it, and then get a more accurate assessment of what your average daily temperature actually is or was. So Goff and he, published a few years ago, looked at a station up in Canada, Churchill, Manitoba, up on the Hudson Bay. This study kind of showed you two important conclusions that informed my work going forward. So one, of course, there is actually a large difference between these two methods of temperature averaging due to the skewness in the daily temperature curve, again, not accounted for in the traditional method. So they average just at a monthly level, and some months you saw a difference between methods of up to 1.5 degrees Celsius, so quite significant. They also saw a strong seasonality. So as we know, the daily temperature curve isn't going to be the same throughout the year, especially a place like here where you have strong seasonality. And in this case, the strong seasonality and the difference between methods, again, born from changes in the nature of the daily temperature curve over time, was due to the fact that they have a strong pattern of fog during certain times of year. Specifically, since the station on the Hudson Bay, when that's frozen over in the winter, no moisture available. But when it is unfrozen in the summer, you have much more frequent fog outbreaks because you can pick up moisture off of that body of water. And of course, combine your air masses and whatnot. So this graphic here on the left shows the frequency of fog sort of standardized to 0 in the blue line, and the red line shows the difference between temperature averaging methods. So you see a large positive difference during the summer months, month numbers here, going along with very high frequency of fog. So essentially, the occurrence of fog, in this case overnight, forming due to moisture from the body of water, the Hudson Bay, skews the daily temperature curve. Notably, basically, it cuts off. Temperature can't fall as much with that additional low cloud cover. And as a result, you have the strong difference between methods. All right, so how exactly do we quantify this asymmetry? So again, the big thing here is we find that in most places, in most times, but not always, we have a rightward skew in our daily temperature curve. So this is, again, that same average for Albany now, just in box plot form. So we see, if we just put the number of hours of the 24 hours in the day into these 2-degree temperature bins, we see that more time is being spent near the minimum temperature and less time is being spent near the maximum temperature. on your given day. And of course, then you can think about how that's problematic for when you just say maximum over 2 is giving you a good representation of the daily average temperature. So in this case, more hours being directly closest to the min versus directly closest to the max. And also, even just in the lower part of the distribution, you see this bin here, for example, more frequent than those bins on the other side, the higher part of the distribution towards T max. And although I didn't use minute data, I just used hourly data, but looking at it for future work, certainly minute data, 1 minute data for temperature would be very important. Here's another example showing this important skew that we see. So this is actually this day last year for Sioux Falls, South Dakota, so a place out in the high plains that often has wild temperature swings. So the black line here is the mean, and then this is the frequency of number of minutes spent at each 1 temperature degree interval. And we clearly see many more minutes, much more time being spent on the bottom half of the range than the top. And again, of course, now that's going to throw off our mean temperature if you're just using the 2 data points, because of course you're kind of giving too much weight to the maximum when more time is being actually spent near the minimum. And of course, the way to put the number on that is the Yule-Kendall index, and just a positive, or Yule-Kendall index means you have a positive rightward skew, and Yule-Kendall index is just simply calculated with looking at our distance from the median or the 50th percentile between the 25th and 75th percentiles. So in many cases here where you have the rightward skew, of course you have the fewer and more extreme values up on the top of the distribution. So your 75th percentile is further away from the median than the 25th percentile, and hence that gives you this positive number, the plus here. And you see it in the box and whisker plot, that rightward tail coming from less time being spent near the top. All right, so why do we care about all of this? So as I've just shown, you have a general overestimation of temperature by the traditional method of temperature averaging, the max of 10 over 2, because more weight is being put on the max than should be. Okay, so why? So why exactly do we see this typical pattern? So getting into actually what I did for this dissertation work and the research coming out of it and the papers. So I just simply utilized hourly and daily temperature data. I looked at the first order weather stations across the U.S. and did the contiguous U.S., just the lower 48, no Alaska or Hawaii. And of course I kept the measurements in degrees Fahrenheit to avoid any rounding issues and losing tenths of a degree due to that. So I just very simply compared the two methods of daily temperature averaging, just max plus min over 2, and hourly divided by 24, so 24 versus 2 observations, and just followed the typical 30-year climatology normal, so 1981 to 2010, again for the 215 first-order stations. Obviously there's a few more first-order weather stations that are used, but some of them, the hourly data wasn't as available in the early part of the climatology, so I had to lose a few of those. And then this was done at an annual time scale, and then at a monthly scale to start getting into the seasonality of these differences and getting at the change of the daily temperature curve throughout the year. And of course did spatial analysis, and I used kriging for all the maps that I'm going to show for the interpolations of the point data. And the general goals and hypotheses, so basically tease this out in the first little part here. So we know that temperature and its daily curve varies seasonally. Of course, we know we have much different range in temperature and nature of the temperature curve here in the winter versus the summer, etc. And spatially too, of course, you know that latitude and elevation plays a big role, not only in the actual temperature, but also in how it can change throughout a given day. Therefore, we should see strong seasonal and spatial signals in the difference between temperature averaging methods, again, as a result of the daily temperature curve variation, and hence analyze and then model the difference between methods. So we should then be able to use basic climate variables to explain these variations observed, and again, all this based on those 215 first-order weather stations used from the first-order data set. So here's the first map here showing the annual difference between methods. So this is 1981 to 2010, just averaged throughout the entire year. the difference between those two methods. So this is the traditional method, max mean over 2, minus hourly averaging. And we note that most of the country, as expected, sees the overestimation by the traditional method due to that general rightward skew. So under the kind of neutral and green colors is positive, so that means you have an overestimation. And you can see in some places this is fairly notable, several tenths of a degree Fahrenheit. The strongest overestimation being along the immediate Pacific coast, as well as the southeast and into parts of the south and the central plains. But we do see very interesting regional patterns, of course. So for example, the Great Basin here we see negative, so a bit of an underestimation. And the same thing in the northern tier across to the upper Midwest and parts of New York and New England. And then there are just a few boxes showing these key regions where we see the spatial variation. Sometimes over short distances, you go from a pretty strong overestimation along the immediate coast of the Pacific to the underestimation here over the Great Basin. And of course, you can start to think about, well, what sort of patterns and physical geography might explain these, and I'll get to all of that soon. There's also, of course, as expected, your seasonal variation. So now this is just some monthly maps. This is just all Januaries for the 30-year period. And notice, for example, the box around the Midwest region. So we see here in January a bit more in the way of underestimation, and you see most of the Midwest an underestimation by the traditional method. Flip to March, and most of that area kind of goes to neutral, so now much less of a difference between methods, except in the far upper Midwest, still an underestimation. So both spatial and seasonal variation all readily apparent here. And now, here's a GIF that's maybe going a bit too quickly, but this shows the annual cycle, as it were, of the difference between methods. So just flashing through each month of the 30-year period. And you can clearly see a very interesting progression here. So if I start talking when it goes back to January, we see in the winter months kind of those purple colors dominate more. So we see a tendency of underestimation by the traditional method. Then the blue and purples, those erode away as you go, especially into summer, late summer into early fall, more overestimation, and then that flips again as you go back in the winter. And of course, the interesting spatial patterns here, for example, we notice that the Great Basin has strong underestimation, then that erodes away into the fall and returns again in the spring and summer. We also see, say, in the south, we see very strong overestimation as we go into summer and fall, and then that recedes away during the winter. So clearly you have some sort of cycle going on here annually, being explained, of course, by cycles in our climate, monthly and seasonal climate. So again, try to explain what physical factors are explaining these, I think, at least interesting spatial and seasonal patterns, as well as what's explaining just the first thing, what's the general asymmetry being caused by in the daily temperature curve, what climate factors are most key in controlling the daily temperature curve. So to go about this, I use just basic climate variables known to influence temperature, and especially its diurnal range, not just temperature, but also how it changes throughout the day. So of course, your classic factors at both the surface and up in the atmosphere, so cloud cover, humidity, but also land use, land cover, soil moisture can also be very important for temperature, and are seasonally dependent, and then of course help to explain those seasonal patterns shown. So I again looked at processes at multiple spatial and temporal scales. So of course wanted to get an idea of what's going on more broadly, maybe explaining some of this. So your progression of air masses, so clearly synoptic climatology is playing a role in these patterns, because you see those large regional coherence in the difference between methods, and then also the progression through the year. But also, as we know, temperature can sometimes be influenced, especially under certain synoptic patterns, most strongly be influenced by the smaller scale things going on. So maybe local cloud cover, or down at the surface, land use, land cover, soil moisture, presence or lack of snow cover, as well as humidity and precipitation modulating temperature as well. So to kind of give an example of all this, I'm going to show a case study here that kind of ties the link between the difference between methods and the daily temperature curve and the climate variables explaining it. So this is the map for the May difference between methods. And note how I boxed in Arizona and New Mexico and put a star roughly near Tucson, Arizona, the station I'm going to pick on here. So we see in May, the immediate Pacific coast overestimation, but just inland in the interior west, we have a broad area of underestimation by the traditional method of daily temperature averaging. Flip ahead into July, and what do we see? We still see in the Great Basin and much of the interior west that underestimation. But Arizona and New Mexico flip pretty strongly from underestimation to overestimation. So clearly your daily temperature curve, the nature of it is shifting pretty dramatically in just a pretty short time period from May to July. So we made a pretty good hypothesis of what's going on here. And this is the inland extent of the NAM, the North American monsoonal pattern, influencing the daily temperature curve, and then we're seeing that play out in the flip in the difference between temperature averaging methods. So now here's the station example for Tucson, Arizona, and a look at the climate variable specifically. So here's Tucson, Arizona, May versus July. So in May, on the left here, negative difference between methods. So we actually have the strange case where the traditional method is underestimating temperature. And that's happening because your Yule Kendall index is actually negative. So in this case, you have the leftward skew in temperature, and we can see that here in the box plot. So now actually more time is being spent near the max and less time is being spent near the min. So kind of a flip of the normal. And flash forward to July, and of course as we saw on the map, now Tucson and most of Arizona and New Mexico go in line with most of the rest of the US during most of the year. Positive difference, positive Yule Kendall index. Now we go back to the normal case as shown where you have the rightward skew and daily temperature. And again, now more time being spent near the minimum. And what's explaining this? It's the NAM, the monsoon, and we can tease that out using some basic climate variables. So we see, for example, during May, our pre-monsoon month, where we have the weird leftward skew in temperature. The synoptic climatology shows very low prevalence of moist tropical air mass. So typically it's a very warm to hot but dry pattern. Minimal cloud cover, very low humidity, minimal precipitation. So the hypothesis then being that more time is spent near the maximum because of very dry atmosphere, you can warm up very quickly through the morning and throughout the day. Then July, early to mid-July, typically the North American monsoonal pattern initiates much moisture atmosphere, and it's very apparent in our statistics here. So the frequency of moist tropical air masses goes up by 6 times, cloud cover more than doubles, humidity on average more than doubles, precipitation goes up immensely. So now you have the moisture atmosphere, temperature can't rise quite as quickly, and the implication now is you have more time being spent near the minimum, and you go back to that positive skew, rightward skew in your daily average temperature, and back to the twice daily method overestimating temperature compared to the more true 24-hourly average. So what I then next did, sort of based on that case study, I just did some simple first overall correlations between those climate variables just shown and the difference between methods, and then eventually went up to building some simple regression models. So trying to model these difference between methods using these climate variables, again, that are clearly impacting our temperature and its daily curve. And interestingly, the magnitude and sign of these correlations between climate variables and difference between methods varies both in magnitude and sign over time and space. So again, the implications of these variables can be different depending on where you are, what time of year you are. Typically, though, as expected, strongest correlations between climate variables and difference between methods during non-transition seasons, so the winter and summer. So obviously, during the transition seasons, you have lots of weird things happening, big temperature jumps, frontal passages, things like that. A little more settled in the winter and summer, so you see the stronger correlations. And also the months when the climate variables are most influential, naturally you see them having a stronger influence or a correlation with the difference between methods. So the ready example of that is snow cover. Shows strong correlation in January and February when, of course, snow cover is most present here in the cone US. And here's one example of the correlation between climate variable and the difference between methods. So this is precipitation. So we see here, first of all, with our climatology, just precipitation on average. So average annual precipitation is what we expect, higher in the east, lower in the west. And of course, precipitation is generally going to be highest in spring and summer months. So June, we see much higher precipitation, especially in the southeastern U.S., and less in February. And unsurprisingly, the months when precipitation is strongest is largest. So those spring and summer months, we see the higher correlation. So those two charts on the right there, on top you have correlation to get up towards 0.5 during the late spring and early summer, which again coincides with when you have the most precipitation on average across the cone U.S., and then it really goes down to very low during the winter months. Precipitation is also generally lower. And maybe other processes are more important for explaining temperature throughout the day. And lastly, in addition to those climate variables, I also looked at another important factor on the daily temperature curve, land use land cover. So I also looked at a land use land cover categorization and classified stations based on the dominant LULC around. We all know that LULC type can have a strong influence on local climate. For example, the urban heat island effect has a very important influence on the daily temperature curve. For example, not letting things get as cold at night. And these airport stations throughout the U.S. are in many different places. Some are very close to big cities and sprawling metropolis, so JFK or LaGuardia Airport. But others might be in very small airports out in the Midwest, where sure you have some very small runways, but then you can be out in the middle of cornfields. So obviously that has a very important influence on your daily temperature. So I use the NLCD, the National Land Cover Database, to categorize stations by LULC type around them. And they just have the basic 7 categories of land use land cover type. And I also looked at different scales. So depending on, say, the synoptic pattern present, sometimes it's the close-in land cover that can be most important, but sometimes the broader land cover. So I looked at the micro and meso scale for that, and compared differences based on land use land cover category. So here's just an example of how I went about this. So here's a National Land Cover Database map for New Orleans, Louisiana, and we see those 2 circles just based on the Orlansky paper of scales. So this is land use land cover at the micro scale, just within 2 kilometers of the station, mesoscale, 20 kilometers of the station. And I just did automated pixel counts. So whichever land use land cover type had the highest pixel count within the circle was deemed as the dominant land use land cover type for that station. So in the example of New Orleans here, we clearly see at the micro scale we have developed land, these different red colors, as the dominant land use land cover type. So it's an airport, also at a big city. The meso scale, you actually have water cover as the dominant type. So you have Mississippi River and the water there off to the north. So here are just the basic numbers on the land use land cover categorizations and difference between methods. And at the meso scale, we saw a significant difference for the difference between methods between all the different land use land cover categorizations, and just below significance at the micro scale, but clearly land use land cover playing a role here. And for example, some types of land use land cover, you see a much larger difference between methods. So developed land and water being close by, being the 2 biggest, and then other land use land cover types, very minimal difference between methods. For example, shrub and scrub land and cropland nearby. So why? So we see here greatest overestimation in terms of land use land cover type dominant around a station occurred at developed land, open water, and grasslands. So of course, developed land and open water, this is very sensible physically, I think. Typically in these places, so in developed land, the urban heat island effect, open water, your specific heat, you have a slower nighttime fall in temperature. Therefore, we have a much more asymmetric daily temperature curve and end up with essentially more time being spent near that minimum because you have that very slow fall, and hence you have that larger overestimation by the twice daily averaging method. The smaller overestimation, these were at both scales, were the shrublands and croplands, so typically I'd say in the Great Plains. So in places like that, so you don't really have developed land around, you don't have big forests, you don't really have anything capturing the heat. So you have a very quick nighttime fall and daytime rise in temperature, so you have a more symmetrical curve, so minimal differences between the methods there. So finally, can put all this stuff together and create some linear regression models to try to explain again these differences between methods and their spatial and seasonal patterns. So initially I just started with those 6 small-scale climate variables mentioned that I was studying. So cloud cover, precip, dew point, humidity, soil moisture, and snow cover. And again, as mentioned, these were most effective during the non-transition seasons, these linear regression models. So I did at the monthly scale, so for each month for the 30-year period. So the winter and summer, more effective. And again, during the transition season, especially the springtime and April specifically, you get some crazy things happening with the average of these climate variables and also the daily temperature curve from day to day. So not as much skill there modeling this, but better skill in the winter and summer sort of core seasons. And all these variables popped up as significant in multiple different months. So here's the giant sort of ugly table showing all of this. So the months and all the variables as significant, and then the adjusted R-square of these models. And you can see definitely some skill here. You know, adjusted R-square around 0.5, 0.4 to 0.5 in many of these months. Of course, significant. So folded in here, we see, again, the winter months, December through February, adjusted R-square around 0.5, and again in the summer, pretty good skill, and then we see in the spring and the fall, very, very low skill, but still some significant variables. And also going back to the fact that variables were typically most significant during the times of year where they may be most important in controlling temperature. So for example, cloud covers, of course, in most places greater in the winter, so we see cloud cover popping up significant in the cool season months, but not really in the warm season months. Snow cover only ran that in the cold season months, and that was significant in all the cold season months, November through April. Snow cover having, naturally, as you expect, having control in the daily temperature cycle, difference between methods. And then some of these precipitation and humidity variables sometimes popping up more in the warm season as significant. And of course, those values are higher and maybe having more of a modulation on your daily temperature curve then. Then, to see if I can improve things at all, I threw in land use line cover into the linear regression models as indicator variables, just which LULC category you were essentially. And unfortunately, didn't really improve the models drastically. I just tested the January and June, the 2 most skillful months. Still, just R-square around 0.5 with the LULC categories in there, but a few of them did pop up as significant, specifically croplands, shrublands, and water, and I picked on those earlier on. So being close to water, especially maybe in the winter, that can be a really important indicator of temperature not being able to fall off as much. Of course, being near the body of water. And then croplands and shrublands being important. Again, those places where you have low vegetation and not much urbanization, again, temperature can rise and fall more equally, and then have less of that asymmetry in the curve and the smaller difference between averaging methods. Then the last thing I wanted to do was to try to put this into the context of anthropogenic global warming, change in temperature, increase in temperature over time. So the last thing I did was to do a comparison of the difference between methods for 2 periods, so my base period of 81 to 10 versus the most recent 15 years, 21 to 2015. Obviously not ideal, and this is a smaller time period, and there's some overlap here. But I couldn't really go back much further than 1981 because the hourly data is much sparser for many of the stations going back further. So at least I wanted to go in times when, of course, you had a lot of data available. So did the 2 comparisons there. Still, you get some new years, of course, in this latter period and are weighting the more recent more. And of course, going along with change, you see an overall increase of 0.5 degree Fahrenheit in just average temperature overall between the two periods. And then you also have some interesting things going on here with the difference between methods. Just looking at the straight up mean or median of the difference between methods, you have a decrease here. So getting closer together. So for the median, it went from 0.1 degree Fahrenheit, lower than the mean, to 0.02 degrees Fahrenheit, so almost getting to equal. But the median absolute difference is increasing from 0.25 to 0.32. So essentially, as mentioned at the open here, most stations you have an overestimation by the traditional method due to that rightward skew. But this change over time is indicating that more stations are seeing less of that overestimation and some are going towards an underestimation. So the median is going down, but overall there's a bigger difference. So overall you have a more skewed daily temperature curve. It's just that some stations are flipping sign to an underestimation. So that's bringing down the mean and median. But this number here is showing that overall a bigger difference between methods, indicating a more skewed daily temperature curve is occurring in the more recent time period. And here's now the maps showing the change over time here. So this first map on the left here is just that 81 to 2010 annually average map. Sorry, for the 2101 2015, so like 81 to 10, just the new 15-year time period, most recent. And you still see similar patterns here. So along the Pacific West Coast, overestimation, same thing across the southern tier of the US. But maybe a few more places now seeing the flip to underestimation. And everyone's seeing an increase in magnitude. And this is just the difference between the two time periods, 81 to 10 and 01 to 15 on the right here. And we clearly see some places are seeing an increase in overestimation. So along the coast, west coast here, Texas, part of the mid-Atlantic. But the broadest thing going on here is over the central US, the Great Plains, you have a negative difference or a flip towards underestimation in many of these places. So what could be some of the physical explanation factors here? So a couple different things going on potentially. So the big regional shift in the Great Plains could possibly be due to the fact that they've actually seen a decrease in agricultural land cover there in portions of the Great Plains. So less agricultural land cover, less evaporation, drier conditions, and therefore you get your more symmetrical daily temperature. So human-induced land use land cover changes, perhaps driving a change in the daily temperature curve and thus change in difference between methods. One other thing that could be confounding this a bit is station relocation. So in the mid-90s, basically all these stations here converted to ASOS, to the automated system versus the manual. And a lot of times when that automatic equipment is put in a different part of the airport. So you had some station moves, many of these stations here in the mid-90s. That kind of cuts my 81 to 2010 period in half, whereas 01 to 15 misses that move. It's all the new location. And even just a slight shift in location of your observation site could be to say a place with different land use land cover, different part of the airport, different elevation. So that could maybe be explaining some of these changes here. It's the fact that all these stations move, so you have a sort of observational bias here. And lastly, when we think about the places where there's a greater difference between temperature averaging methods in the new period, well, perhaps daily temperature curve changing with time is due to the fact that overall, of course, we have warming and more moisture content in the atmosphere. So perhaps a moisture atmosphere meaning a slower daily temperature rise, and again, reinforcing more time near T-min. So a broad trend of increased rightward skewness, but in certain places like the Great Plains where you have a drying due to the land use land cover change, you have the opposite going on, a flip towards a more symmetrical daily temperature curve. But clearly some changes over time here and overall climatic change perhaps playing a role in our daily temperature curve. So some concluding remarks here. Obviously the broad points here, so clearly we see there's a difference between temperature averaging methods. In some places it can be of several tenths of a degree Fahrenheit. In some individual months for individual stations it can be well over a degree Fahrenheit. So this is a very notable difference here between the two methods. And obviously the latter, the 24-hourly, being a more accurate method. Of course we see important spatial and seasonal variation across the CONUS. in these differences between methods. And these variations are being caused, of course, by progressions in climate variables, seasonal progression, spatial variability. Therefore, we had some success modeling the difference between temperature averaging methods using those basic climate variables known to influence the daily temperature, and specifically the nature of its curve. And of course, it's quite important to have a better understanding of the difference between methods to hopefully motivate us to switch to using this hourly method for, say, developing our baseline 30-year normals and thinking about how we calculate, say, indices like heat index, growing degree days, and those sorts of things. And as we know, understanding the daily temperature curve and how it's changing is very important. Not just average temperature, but also the daily temperature curve is important for human systems, say heating and cooling, and also natural systems. Some plants and vegetation are very heavily influenced by the nature of the temperature and how it progresses through the day. So really important to understand how this daily temperature curve is changing, and one good way to think about it is through comparing these two different methods of daily temperature averaging. And lastly, I teased a bit the minute data, and with the increase in mesonets here in many states, including New York recently putting in the mesonets, as that data becomes more available for more amounts of time, clearly sub-hourly analysis will be possible. So averaging maybe every minute of data throughout the day, how does that daily temperature curve look, and how is that different from twice daily and hourly averaging? So again, much of this work was done as part of my dissertation, so I have to acknowledge my dissertation advisor, Andrew Carlton, as well as the committee members for all their feedback and all the time spent helping me out on this. And again, an initial paper on this is in a second round of revisions for Journal of Climate. Another paper is in submission as well. And thanks to Brian for hosting me and arranging this whole visit. And thanks for your time.
Okay, we have time for questions. Ron.
Yeah, very nice, because I never realized this problem. Usually when I kind of use climate model, it computes basically actual mean.
Right.
And compares it to not like say recent observations, which also kind of maybe, but probably those data sets use this old way of.
Yeah.
And I always see this systematic biases, almost exactly like your mind. And so people actually probably don't, I don't know if they realize, and so they try to tune their model to actually make it more like observations, even though they're basically comparing two different things.
Yeah, if you're doing apples and oranges.
I think many people don't realize this. I think it's very nice.
Yeah, I know it's a really simple question, but then people forget about it.
Right.
So, yeah.
They treat data as like data without even knowing what it actually is, and, how it's computed.
It was just a comment on that. The model biases are much bigger than the magnitude that you're showing.
Yeah.
No, it depends on the model.
Yes, depends on the model, but most models actually are biased by a few degrees over, for example, over the US Great Plains. Most of the models are biased by a few degrees rather than 0.5 degrees. Well, simplified models are, so maybe your model is much better. So because I think most GCMs, they are not really tuned into the 0.5 degree type of range.
But still, it's still a appreciable kind of, many people just don't even realize this,
Yeah.
And who knows what, like some models can be, and people actually try to understand what's wrong with their models, why such systematic bias, but actually maybe there is no such systematic bias if you compute it differently. I'm pretty sure that in the models, if they don't compute it like this, minimum plus maximum divided by 2.
Yes, I think you would be very telling if you can look at the short wave of the solar radiation and the infrared radiation. I would imagine there would be a lag of precipitable water, like the total moisture, relative to the surface temperature.
Right.
So if it's really the short wave, then say there would be asymmetric temperature change in one direction. If it's a long wave, it will be in the other direction.
Yeah, definitely. I didn't really get at the the sub-monthly variability. But
And I think like ARM, the DOE ARM program should have this kind of data
yeah.
for you to.
Yeah, great, thanks.
What I wondered, I think you mentioned in a way, in a tangential way, but when you are looking at the possible physical variables, you didn't mention wind. Why?
Yeah, that's a good point. Certainly wind can play a bass. For whatever reason, I didn't end up using it. But yeah, wind, obviously, the nighttime especially, and mixing and all that. So yeah, wind would definitely be a factor there too. I'm sure I threw it in at one point. It just didn't maybe seem to have a big impact. Because obviously, wind can be problematic, I guess, in some ways. The direction and the advection and everything. But yeah, certainly it could be considered.
So you compared the differences in temperature between two different periods. Have you compared the interannual change? Because I think, for example, for North American monsoon has interannual variability. I'm curious how much.
Yeah, I think that would be kind of the build up. I did like the standard deviation, like the monthly, and obviously some places show more variability than others, and yeah, like the Great Basin area to the south had the high variability because of, say, the monsoon. But yeah, kind of looking at the sub-seasonal would be important.
Or whether there's a trend, right?
Yeah.
I mean, you took the subtraction, but I mean, it'd be noisy, I'm sure. It's small trend, but the question is there some change that would be defined and really.
Yeah.
So,
Yeah.
Right.
Oh yeah, I'm sure.
Yeah, I actually thought when you posted the spatial plots, it was really interesting that just from a very cursory glance at it, it seemed to follow the moisture, and you went into more detail about that. There was this just like first order link between moisture just by looking at it.
Yeah, exactly.
Have you done any correlation plots with any variables, whether it's specific humidity or any moisture, with these plots, with this data, to see different levels of correlation, whether it's monthly, annually, or even within the?
Yeah, I didn't do it spatially at all, which I'm sure would be useful. Like I said, I just did the basic, monthly overall. But yeah, certainly like on the precip here. But maybe I passed. Yeah, but yeah, certainly. Yeah, kind of a principal component sort of thing would certainly be useful to build off. Yeah.
But based on this, can you actually correct data sets or?
Yeah, yeah. I was thinking, yeah, you
so
could.
that models could compare, their way with.
Yeah, it could develop a bias correction based on the annual, or really the monthly, I guess you could apply for each month if you trust 30 years worth of data being the absolute way of how it's skewed or whatnot. But then you have this problem of the change over time. So.
Yeah, I was curious about. I mean, your regression was okay, or moderate correlation.
Yeah.
I guess I was surprised it wasn't a little higher.
Yeah.
I was wondering why it wasn't higher, and whether it was maybe not needing solar radiation, some other variable, or.
Yeah, I tried.
Or it's a synoptic variability of understanding whether a day has a certain pattern.
Yeah. I did this with the air mass climatology as well. So it's kind of like the frequencies of the different. But of course, that's just derived based on these variables too. So it kind of. And a few other people have approached this problem and got fairly similar correlation coefficients. I think maybe if I did this at the regional level, it'd be much higher. Like if I just took, if I just took stations at certain regions, it could be higher. But remember, they're trying to kind of throw this for the whole CONUS, so there's lots of noise and lots of stuff going on that brings down the skill.
Is the daily defined the local time from 0 ZZ to 3 4Z, or?
Is local standard time.
Local standard.
Yeah, midnight to midnight local. That's how the U.S.
Okay, I'm thinking that from 0 to 24, we see 2 days.
Yeah, but I mean,
thinking whether we can use 2 minimum.
Right.
Consecutive days minimum, and then 2 maximum 1 day before numbers, together divided by 4.
Right.
Solve the problem.
Yeah, there's different algorithms developed to do that sort of thing.
If not, let's thank Jase
Thanks.
again. Just a couple announcements. We have lunch